quickly move to the next speaker, who is Andrius from EUROnanoLAB. Andrius, until tomorrow, is still our vice chair.
Yes. Yes. Hello, I will be representing EUROnanoLAB. So I will be representing EUROnanoLAB. So a bit of us and what kind of techniques we offer in RIANA. So in RIANA, this is the famous RIANA key that it gives you access to all of this beautiful stuff that you can do in nanoscience. And we are a very small part of it. We are giving access to clean rooms, but clean rooms are very vast usually. We have many techniques, not only for fabrication, but of course, this is the main focus of our institutions. So to fabricate whatever you would imagine of. So we have 44 clean rooms in the network. We are spanning over 14 countries from the south to the north in the whole of Europe, as you see. We have some very interesting missions that we want to make more accessible for all to create their own technologies, to streamline these technologies, to get a better and faster acknowledgement and faster creation of their desired nano scale things. Yeah, so of course, when we are speaking about nanoscale things and their manufacturing, lithography comes into mind, probably the first one. From using sources as electrons, lights, even going to focused ion beams. These technologies are different in a way, of course, but mostly some of them are more research-like, and some of them are more like can be adjusted to for a high throughput, and we can even talk about a high volume technological process that can be even used in manufacturing. So this can be done together with institutions and to creating the whole process for your fabrication, even for a product or something like that. Of course, where there's lithography, there's etching. So different kinds of etching. But if you're talking about precision, we're talking about, of course, reactive ion etching or deep reactive ion etching, because it gives you the most anisotropic, most selectivity, the cleanest lines that you are planning to do. And of course, but they are a bit slower. So other techniques are being offered also in the network, like wet etching, which has one of the best probable selectivities when we're talking about removing materials. And of course, gas etching, which is also very high selective, but not real, very non-complex, but it is usually very slow and fully isotropic. There are many different kinds of depositions. So when we're talking about physical vapor deposition, we are talking usually about sputtering. So there are two types of sputterings, magnetron and ion. These both are very similar, but only the changes are what kind of materials we can sputter with them, basically, and how much is the control of the film or films that we are creating, what is the contamination of them, and so on. Other ones are, let's say, simpler, the thermal processes. So the typical thermal process it's very low cost and it's very fast. But it is limited with temperature problems. So usually high melting point materials are hard to evaporate. So that's why we use electron beam them evaporations. But also similarities with electron beam, we can use a pulse laser deposition, but both of these techniques have a problem that they can spit out material and destroy your samples, basically. There are also chemical vapor depositions, which is enhanced with gases inside of them. We have different types: atmospheric pressure, low pressure, plasma enhanced, atomic layer deposition, and metal organic CVD. So of course, maybe from all of these, the most different is the atomic layer deposition, because it has extreme precision for all the parameters that you would think of for your deposited layer, and it is very low temperature, so it is easy to control. There's no damage formed by plasma. There's no damage formed by heating up, and so on. But it is, of course, the most expensive and the slowest of them all. There are other techniques for other types, but these are usually the supporting techniques that we are using for other applications that we could use, like spin coating for photoresists, or even sol gels, or any other materials, even biomaterials, and so on. Of course, we use also 3D bioprinting, and that can be used for creating similarities with biotissues that are can be mimicked in a lab. Looking further, of course, we are talking about also supporting techniques for like packaging, so wafer bonding. So this is a technique usually used for people who are more inclined with micro and nano electronics. So for creating layer structures and many others. Of course, when we are talking about manufacturing, we need to know how to process the things. So we are how to cut out the formed, let's say, nanochips or microchips out of the wafers. And of course, how to then connect them to the whole circuit. So we are using wire bonding. And these are also some supporting techniques that we are also using when we are in need to change materials or clean them, because a clean surface means a very productive technology that can be made. We are also doing a lot of characterization that there's already was spoken here. Of course, maybe not at that level. That's other infrastructures give, but this is very important because we are talking about the process from manufacturing to even characterizing your nano objects or micro objects in a specific way, so we can make sure that the quality is on the right path. Of course, when we are talking about materials, we need X-ray photos, XPS and XRDs, so we can know what kind of structures we got. And if we're talking about more soft materials, we are using Fourier, infrared transformations, and Raman spectroscopies, and others like spectroscopic ellipsometers when we're talking about thicknesses, and when we have the options for simpler measurements, profilometry is okay. There is also other techniques that are in other organizations like pump probe, excitation of materials. So we can talk about the electron dischargement in the materials, how they are affected by light. And of course, we have some destructive measurements, so like SIMS, but also some light measurements where we can change or influence light and how it affects your, let's say, nano-optics that you are talking about, metal surfaces or metal lenses, anything in that vicinity. So thank you for your attention. I am from Lithuania, and I have my colleague, Octavian, who is from Romania, and we are both representing EUROnanoLAB here.